Today we are going to see how to make your filters run fast in PyTorch while still being differentiable. And the techniques I will show today are implemented in a package I made called PhilTorch. So something about me, my name is Jingyun. I'm a PhD student at Queen Mary University of London in the AI and music program. I research things including music information retrieval, voice synthesis, audio effects modeling, and binaural audio synthesis. And here's my website link. I have been looking into the problem of making a differentiable filter run fast for a few years now. So this talk is a summary of some of my publications on this topic in the past and some blog posts I wrote about this. All the materials are from there. Okay, and here's the agenda for today's talk. We're going to see what are differentiable filters, the efficiency problem in PyTorch, my proposed solution, some benchmarks and tips for efficient usage of this package. Anyway, let's get started. So, what are digital filters? Any linear time invariant discrete filter is characterized by its transfer function in the Z domain like this. This is a very textbook example. It has two polynomials with B and A coefficients. If we directly convert the function into its difference equation in the time domain, we get the second equation where x is the input and y is the output indexed by time index n. And this is called the direct form filter, very basic form to build various digital filters. Each output step depends on the past input values and also the past output values, forming a recursive system. Filters, they are very widely used in audio applications, like all kinds of pass filter, peak filter, shelving filters, equalizer, subtractive synthesizer, phasor, linear prediction filter, many of them. It's a very common building block. But why does making it differentiable matter? So differentiable filters have attracted considerable interest from people working on differentiable DSP, often called DDSP. The concept of DDSP is to utilize signal processing components as differentiable building blocks within the neural network and jointly optimize them using gradient-based methods. This approach provides a more interpretable structure to tweak and also to adjust. Also, it introduced strong inductive bias into the model's behavior, so you can save computational costs and some parameters. A few examples here. So in the past, in some publication, we did try this on gray box virtual analog modeling or even synthesizer parameter retrieval by just using neural network to predict the filter modulation parameter and then using the output directly match the raw audio and just minimize the loss. So you can do something with that. Okay, so let's get to the main point of this talk. What's the problem with using these filters in PyTorch? The problem is that PyTorch native operators don't support recursion, or I would say autoregression. It only supports a limited set of filters such as convolution, which corresponds to the B coefficients. For the A coefficient, which introduces a recursion to the filter, there is no equivalent operator to this state. It's a PyTorch team, they are working on that, but it's not ready yet. Yeah, you might argue that we can just build a recursive filter from the ground up using the available operators we have. That's true. And the computation is also differentiable. But the problem is that it takes super long time to run. This is because in this way, the filtering process is split into many small kernels. Before each kernel launch, there are overheads from the Python interpreter, memory allocation, and a bunch of other PyTorch framework overheads. These overheads interleave between kernel launches and giving hundreds of thousands of audio samples, a very typical number for an audio clip. These overheads soon adds up and consume the majority of the runtime, making the entire process extremely slow. In contrast, the convolution operator in PyTorch is implemented as one kernel, and the number of kernel launches is just one, and no matter how long the sequence is, it doesn't introduce any extra idle time. So to solve this slow computation issue, I made PhilTorch. Is a Python package for PyTorch. It features fast computation of linear filtering, set numerical robustness of SciPy, support both reverse mode and forward mode automatic differentiations, all the LTI filters and also support time varying filters as well, which is quite important if you want to learn the modulation and automation in DAW. And due to limited time, I won't cover formal differentiation and time varying filters, but many of the techniques I will show later can be applied to them as well. You can check the package on PyPI and GitHub. I think the layout kind of went off because of, yeah, anyway. So here's a list of concepts I will cover later. We are going to see state space representation, writing custom operators for PyTorch for recursion, gradient backpropagation, and lastly, how to parallelize the filter so we can leverage GPU, which is the default hardware for deep learning. Okay, so first, let's talk about the state space representation. PhilTorch uses SSM internally for two reasons. First is a very flexible representation to represent different direct form filters or even other filters. For example, here's the parameterization that equals the direct form filter I showed before. And second, and most importantly, it enables parallel processing on the GPU, which I will talk later. And the first equation, pay attention to that, is where the recursion at, which involves the A transition matrix and B matrices. Okay, regarding the flexibility of representing different direct form filters, in the past, there exists a mismatch between the L filter function in Torch Audio and the one implemented in SciPy. SciPy is widely used by the research community, and SciPy uses transpose direct form filter 2, which is more numerically robust than the direct form 2. And these two forms actually have the same flow diagram, but the signal flow directions are reversed. So that's why it's called transpose form. In SSM, we can switch between these two forms easily, just replacing the A matrix with its transpose and swapping the B and C matrix. So in PhilTorch, you can switch between these two behavior easily, and the response are the same. Okay, next, as I mentioned before, the fundamental solution to reduce framework overhead in PyTorch is to implement the filter at the kernel level. So the function call overhead will remain mostly the same. In PhilTorch, instead of implementing the entire SSM, we handle only the recurrent part and implement it in C++ and CUDA. In the later slides, by the way, I will use different colors to mark the input and recursive output variables in every recursion you will see later. And to make the kernel differentiable, in addition to registering the forward pass of the filter, you also need to define how to compute the gradients during backpropagation. If you want to support forward mode, then the JVP function must be implemented as well. So depends on your use case, probably 2 or 3 functions are needed. So how to backpropagate the gradients? You have to do some math, and no worries, I did the math for you. So it turns out the backpropagation of this recursion is also a recursion, but with a transposed A matrix and reverse time filtering. And once this recursive filter is evaluated, the gradients for the rest, the input, coefficient, initial conditions are trivial to compute. And this property actually helps to reduce the number of operators in PhilTorch. So you only need to define one kernel, then you can compute all the forward pass and also the gradients. Okay, good. Now we remove the overheads from the PyTorch framework. Is there anything we can do to the kernel for further acceleration? Yes, let's look at the recursion again. You might think it's a recursive definition, so it can only be computed sequentially in an order. However, this recursion, actually, we can re-express it into an accumulation operation over a sequence using an associative binary operator. In this way, then the computation order doesn't have to be sequential. It can be arbitrary order. And you can even compute partial results in parallel and then combine them later. And there's an algorithm called parallel associative scan that does precisely that. In PhilTorch, we use the 6-scan implementation in the CUDA toolkit, so it's very optimized and super fast. And moreover, there's one more thing we can leverage. If the A matrix can be decomposed into a diagonal matrix with poles on the diagonal and an invertible matrix, which means that the filter has distinct poles, we can reformulate the recursion into this new recursion here, where the A matrix is replaced with diagonal matrix. So the matrix multiplications are reduced to simple element-wise multiplication, which can save significant computation when the filter order is high. And there's a different way to interpret this. You can imagine is just computing multiple first-order filters in parallel and sum the output together later. Yeah, I think all the techniques I show are about writing custom kernels. But lastly, I want to present an alternative method that doesn't involve custom kernels and instead just use the PyTorch Python API. So if you don't want to write C++, there's still a way. It's based on a talk by Andres from GPU Audio in ADC 2022. It's called Simple Unrolling. And the idea is that we can augment the matrix in the recursion to predict multiple steps at once instead of one step at a time. Thus, we can reduce the number of recursions and leverage PyTorch efficient matrix multiplication. So it's way faster. But the problem is that the algorithm is still sequential. It's made for online computation. But we are interested in offline acceleration in PhilTorch. Think about it. If we remove the requirement that each sample has to be processed sequentially, can we make it faster? So it turns out we can have an offline version of simple unrolling. And this version is simply dividing the previous equation into two steps. So in the first step, instead of computing all the outputs in one chunk, we just compute the last step of the chunk, which is enough to calculate the next chunk. In this way, the matrix size in the recursion are smaller and faster to compute. And the output will be a subsample version of the outputs. How about the rest of the output step that we skip? So when step one is complete, the rest of the computation can be done in parallel, actually. And by the way, you should notice something in step one. So what's step one? It's a recursive filter, right? And we are talking about accelerating recursive filter. Can we apply the same technique and solve the step one recursive filter again? Sure. So actually, this offline version algorithm actually can be applied recursively to reduce the recursion step even further. Okay, so it's probably kind of hard to imagine, so I put a diagram here. So the recursive algorithm I just present actually is the parallel associative scan algorithm. This diagram was a copy from Wikipedia. So you can interpret this diagram as a sequence with 16 elements from left to right. And we hop every two samples in step one. We apply step one 4 times, and then we recover the whole sequence in step two 4 times. And you can see that when we have enough parallel processor, then the number of computational steps become proportional to the sequence length logarithmically instead of linearly. And this implies that the longer the sequence is, the more speed up we can get using parallel associative scan. So that's super fast. Okay, just some brief takeaways. So if you have your computation have more than 1,000 small kernels, then it's better to write them as a just single one kernel using custom extension. And if your computation is associative, then there's probably a chance that you can make it parallelizable. And you can do both to get optimal speed up. Okay, so that's enough for the techniques about accelerating. And lastly, I think probably everyone is only interested in the number and some plus, so I show some benchmarks here. So to compare the speed of all the methods I showed before, I did a very simple benchmark. The methods I compare are the naive method using just for loop, using all Python API, the optimized SSM kernel, and also the diagonalized version of it, and simple unrolling I just showed. I use a second order filter, a very fundamental building block for any higher order filter. I benchmark the runtime on an i7 CPU and an RTX 5060 Ti. And you can see that by just using a custom kernel, the SSM is already more than 100 times faster than the naive for loop method. And on the GPU, you can see that the difference is way bigger since we can leverage the super optimized parallel scan. And simple unrolling is around 10 times slower than SSM because of the PyTorch Python API and those overheads, but it's still super fast, way faster than the naive one. And this is for the forward computation. The most important part is actually the gradient computation. So let's look at the backpropagation time. So in this chart, the naive method is even slower. So it just went off the chart. You couldn't see it on this. So it's just like very high. So while all the other methods perform comparably fast, yeah. And on the GPU, we found that the fastest method is still SSM, not the diagonalized version. But I think it's probably because the order is like only second order. So if you have way higher order filter, then probably the diagonal version will be way faster. Okay. Yeah, I think we have reached the end of this talk. Finally, some tips for using PhilTorch. Currently, it has very optimized kernels for first and second order filters, which is enough to compose any higher order filters. You can use either cascaded second order session or even parallel second order session. That will be the fastest one. If you just want to know how to use the package, I actually have a very simple example on the GitHub repository. It's about estimating the low-pass filter parameters using data-driven method by just matching the audio. It's very intuitive, and you can see that it's like, here's the plot is the training progress and the estimation progress of the cutoff frequency of the low-pass filter and also the Q factor. So yes, so that's my talk, and that's pretty much it. Thank you for listening.